Welcome to another exercise in the workbook Statistics. This time I'm going to talk about how to test for stochastic independence and provide a respective exercise. So let's have a look at the exercise. Here we have a group of men and women is asked whether they know the series Cheers and Friends. The answers are summarized in the table below. So here we have for male and female, how many knew Cheers, how many knew Friends. Then our task in this regard, use a suitable test, acceptable margin of error of 5%, to check whether a significant relation exists between the participant's gender and the noun series. Well, this is more or less directly what we can use the chi-square test for, because we have, in this case, a contingency table, which more or less invites the calculation of a chi-squared statistic. Well, if we want to calculate chi-squared, the first thing we need is to actually expand this table. So I'm going to copy the table as was in the exercise and add one column and one row. There I'm going to put the column and the row sums, which is more or less then what we call the marginal frequencies. So I'm adding up for males both answers to Friends and Cheers, for females the same thing, and then I'm doing this for Cheers and Friends as well. Finally, on the lower right, I'm going to put the overall absolute. So I'm going to add these two or these two, giving me in both cases 150 observations, 150 people in this sample. Well, that was the first part we needed. And those marginal frequencies we can in the next step use to calculate the so-called expected frequencies. The expected frequencies are the frequencies which look like this, which more or less describe the distribution if only the marginal frequencies are valid and the rest is more or less uniformly distributed. We can calculate them in a relatively straightforward way. We simply, for each entry, take the column sum and the row sum. So here we take the 70 and the 33, multiply them and divide them by the overall number of observations, the 150. So here we get, as an expected frequency, 15.4. Then we do the same thing for the other ones. So always row and column sums multiplied, divided by the overall number of observations. We can, however, interpret this also in a different fashion. We can imagine that there's a rectangle with 4 corners. One corner is actually what we want to calculate. Then how we get this is we take the two adjacent corners, those two. So if this is the rectangle, this corner, that corner, multiply them and divide this by the opposing corner, which always is the 150. So always take a rectangle, this being a fixed corner, this being the corner which we actually want to calculate. So there's different ways how to get these expected frequencies or how to imagine these expected frequencies. Once we have them, we can compare them to the actual frequencies from the exercise. That's why here I summarized expected and actual frequencies. So the first value is always the actual frequency. The right value is always the expected frequency. To compare them, we're going to use the chi-square statistic. So basically for each entry in this table, we're going to calculate this expression and then we're going to sum all of this up. That's actually what the two sum signs mean. We're going to calculate each entry and sum all of this up. Well, what's this supposed to be? This is the expected frequency. That's the actual frequency. So we're always taking the expected frequency, subtract the actual frequency, and this difference is then squared. Finally, this squared result is divided by the expected frequency. Well, this looks a bit more intuitive once we see this with numbers. So for the first part, it's 15.4 expected frequency minus 21 actual frequency squared divided by 15.4 expected frequency. And we're going to do this the same way for females and shears. Expected minus actual squared divided by expected. And similarly here and here as well. So in other words, we have 4 entries in the table. We get 4 terms we have to add up. To not lose the overview, instead of writing it down in this fashion, you could also copy this table once more and then calculate in each field the corresponding part of chi-squared and finally sum up all of these entries. This helps you keep the overview. Did you actually consider all of the entries and not one entry, maybe twice? So there's 2 ways of actually getting this last step done. In either way, we're going to calculate the final result, the final sum, which here is given as 4.8952. So that's not only the chi-squared for this table, this is also our test statistic for the chi-squared test we're going to conduct. And when we conduct a test, we also need a reference statistic. So that's what I'm going to do on the next slide first. So here, just as a short repetition, that's our test statistic. The reference statistic for the chi-squared independence test we get as chi-squared I minus 1 times j minus 1. I is the number of rows, j is the number of columns. Here I have 2 rows, 2 columns, so it's 1 times 1, giving us the first one here. Then I have 1 minus alpha. Alpha, that's the margin of error. Here we had a margin of error of 5%. So we go 1 minus 0.05, giving us here the 0.95. So in other words, in the table for the chi-squared statistic, we're going to look up the value for chi-squared 1, 0.95. There we find a value of 3.8415. So that's the reference, that's the test statistic. So for our test decision, we're going to compare those 2 statistics. And we see in this case, the test statistic is slightly larger than the reference statistic. This means our H0 hypothesis can be rejected. H0 in the context of the independence test means there is no relation between the 2 variables. Since it can be rejected, the opposite is true, meaning there is a significant relation between the 2 variables, between participants' gender and their knowledge of the series. And well, that then answers our initial question and concludes this exercise. I hope you enjoyed it. I say goodbye and see you next time.